A request came in today for a little bit of extra help on the energy calculations lesson 4 that you've got set for this week, due on the 17th of June, and I thought I'd have a go at a bit of live modelling. I am doing this under a bit of a time pressure, so it might not be perfect. You might have to bear with me a little bit, but I hope very much that it will give you a hand if you're stuck too. Okay, I'm going to go through the example one first, just so that you can follow through and make sure you're happy before we get into the equations that I was asking you to try. So in this example, we're told the specific heat capacity. I'm checking immediately to check the units are the standard units. Joules, yep. Per kilogram, yep. Degrees Celsius, yep. All standard. So this is C in the equation that we find on the formula sheet. Now I can calculate the energy that's needed. That's the delta Q, that change of energy that's required to make the change of temperature happen. I can do that if I know the mass, which I'm told here, so that's M in our equation, and the change in temperature in degrees Celsius. So I need to work that change of temperature out. So I've done that in my head without a calculator. If you knew me well, you'd know why I'm so proud of that. I've got that ready. So all I've got to do now, because in this equation I don't have to do any rearranging, I just substitute the numbers in. So instead of M, I've got 2. Instead of C, we can add in the value we've been given, and we've worked out the 50 degrees Celsius. Then I am going to use my calculator, and I'm going to work out the answer. And to finish that answer off, I'm going to remember that energy is measured in joules. Okay, so here we are then with the first example from checkpoint 3 that I asked you to try. In this example, we are being told the specific heat capacity of brick. Checking the units: joules standard, kilograms standard, degrees Celsius standard units for this equation. So that 840, that is my specific heat capacity, that's C. Calculating how much energy is stored. So this is going to be a time when we won't have to think about rearranging the equation, because it's delta Q that we're looking at, the change in energy. Here we have our mass in kilograms, so that's all good, 800, and then we know that these bricks are 40 degrees above the air temperature, so the change in temperature is already given to us, and that is 40 degrees. Therefore, if I substitute into the equation, I have 800. I multiply that by the 840. I multiply that by the 40. And yes, I'm using a calculator. 2, 3, 4. I think I've got that correct. On my calculator I get my answer. All I have to do now is think, what do I measure energy in? And pop the joules on the end. So this example, question 2 from checkpoint 3, is much trickier, because now we have got to get into rearranging the equation, and there are 4 parts to the equation. So there is more than one way to do this. Let me show you one way to do this. We are being asked to calculate the temperature change. So that is the delta theta 1. We're being told the change of energy, which is delta Q. We're being told that in standard units. Fabulous. We're being told that that's being transferred to 1 kilogram of mass. Standard units again. And I apologise for the formatting error from transferring my work from Word, where I write it, into Google Docs and not spotting that before I uploaded it for you. Sorry, back to the question. The specific heat capacity of the brick is in standard units, and we've seen that one before. We recognise that one. That, of course, is C in our equation. So this time we know delta Q, we know M, we know C, and we're trying to find the change of temperature. So let's substitute in what we know. We've got 25,000 joules of energy being transferred to 1 kilogram of this particular specific heat capacity, and we're trying to find out how much its temperature will change. we can now solve this part of the equation, and I can do that in my head. Stop laughing at me. There we go. I have now got that equation down to 3 parts, which if you like triangles, you're going to love the fact we can now use one. Okay, if I was to cover over the 25,000 with my finger, I need the triangle to show me to do 840 times the change of temperature, so they have got to go in the bottom of my triangle, but it wouldn't matter which way round I wrote them, which leaves the 25,000 in the top of my triangle, which means when I cover over the thing I'm trying to find with my finger, I'm left with, if I want to work out the change of temperature, I need to do 25,000 divided by 840. And of course I'm using a calculator now. Let's check. It's 29.76, and that change of temperature will be in, a reminder here, degrees Celsius. So that's one way to solve that problem. There is another way you could solve it. So I've gone back to the step where we'd identified, highlighted the relevant bits of the question and recalled the equation. Sorry, I don't mean recall, do I? I mean chosen the equation from the formula sheet. But we've chosen which equation we're going to use. Now you could rearrange the equation first, and you could do that mathematically. To do that, you're trying to keep this change of temperature as the subject. So at the moment, mass times specific heat capacity, this bit, is in our way. To get rid of it, you do the opposite thing. So if you take the mass times specific heat capacity and divide that, we'll be able to cancel it out and get rid of it. But we can only do that if we do the same thing to both sides. So over on the other side, I need to divide by mass times specific heat capacity. Then I can cancel these out. And what I'm left with is, if I want to work out the change of temperature, I need to do the change of energy that's been divided by the sum of the mass times the specific heat capacity. And then I can put my values in. Bear with me while I do that. What is it? 1 times 840. And then with my calculator I work out the answer. Don't you wish I had kept that in front of me, so you didn't have to wait while I did it again? And that change of temperature needs a unit adding on the end of it. So you could rearrange the equation first mathematically and then substitute into it, or you could substitute the numbers into the equation, solve what you can, and then rearrange it. There is an advantage to doing it the first way. If you substitute correctly into the equation, but then you mess up rearranging it, you're still going to get marks for substituting correctly into the equation. If you rearrange incorrectly and then substitute into it, even if you substitute in the right places, they're still wrong, so you're not going to pick up any marks at all. So I would recommend doing it the first way. If you really want to, you could turn this equation into a triangle, but you have to lump together, like I did when I was cancelling out. You have to lump together the mass times the specific heat capacity here. So if I was making a triangle for this, I would have to have my change of temperature at the top, change of energy at the top, and have that divided by the mass times specific heat capacity in this corner, and the change of temperature in this corner. I don't like it. I'm not a big fan of using triangles for 4-part equations. I would much rather you substitute in, solve what you can, and then if you like triangles, use it at the point where you have got 3 variables left, 2 numbers, 1 letter. I hope that helps. And if it did, you might want to have a look at the extension questions, which I'm going to make a quick video in the same style right now.